All right. Hello, everybody. We are currently now in session number 7 of the class. And, last time what we did was we looked at some historical transactions, retail transactions, and we worked with trying to cluster the customers. We wanted to segment the customers by purchasing behavior. And so we looked at the customers and clustered them by how often they came to the store and how much they spent, right? And then we showed multiple ways of grouping them. Well, today what we're going to do is we're going to use that same data set, but we are going to try to answer a different question. Since our data is actually at a very detailed level, right? We see that our data, we have it by invoice, and in every invoice we can see every item that was part of that invoice. So one of the questions that is commonly asked is that when you buy a specific product, then is there a way to figure out whether there's some other product that typically goes well with it, right? So this is also called bundling, right? So we want to figure out, can we come up with some bundling recommendations, okay? And we already have the data for that, so let's go ahead and get started on trying to do that, okay? So let's first bring up the data, and then after that we'll go and try to think of how we're going to do it. All right, so initialize here. First thing we would do is load. Probably only need pandas for this. We're not going to be doing too much visualization. And we're going to be loading the same transactions data that we used last time. So called retail transactions, and it was in the retail folder, and then retail transactions. And if you remember, we had to encode it with an ISO encoding because of the special characters. So let's do that. Use ISO A591. That's the encoding we use. Okay, and so if we again take a look at the data, this is what we would see, right? So you've got invoices and then items that were in one invoice. And so what we're really looking for is if there's many invoices or many occurrences where, let's say, whenever somebody purchases a heart tea light holder, or a white hanging heart tea light holder, then they also purchase Cuban hearts coat hanger or something, right? So we want to look for many occurrences of those and then start making those types of recommendations. Okay, so since we're primarily interested in this column, let us see one thing that we would want to do. We need to clean up the data a little bit. So for example, we're going to be using the description as is, so we want to maybe get rid of spaces, maybe get rid of any special characters like periods and stuff like that. Okay, so let's go ahead and do a little bit of data cleaning. So create data, and in the cleaning, right, so first we'll create a different, whenever we do preparation, it's always a good idea to create a new column to hold that in case we want to change the way we clean the data. So clean description, right? And so we're going to take our description column. So we'll initialize it with whatever we have in the description, and then right, so let's just see what this looks like now. Okay, so we just got a new column here, same value as description. So now let's add something. Let's replace all the spaces with underscores maybe. Okay, so let's say and replace space with underscore. There's many ways to do this, by the way. So one of the ways, so you can do the dot replace. Okay, here we go. Dot replace and space with an underscore. Regular expression is a special way to, those of you who know regular expression, you can use regular expression also to do this replacement. But since this is a basic one, just a string replacement, we can just go with a dot replace. Okay, so let's take that. Okay, so we'll say if and we want to replace only clean description. That replace and okay, let's do that. And let's set that equal to the change. Okay. All right. So if we do that. Okay, so it's trying to do the replace. Oh, right, so we didn't put this in quotes. Okay. So the clean description doesn't seem to be changing here, right? It's still got spaces. So that might be because of a type issue. So let's take a look at what the type of this. So let's say df types. Oh, so clean description is an object. It needs to be string for us to be able to apply this replace. So let's do a SDR here. So it's a conversion for string and then a replace. We run that. Perfect. So now you see that our clean description has underscores in place of the spaces. But we also have these special characters. So we can do the same thing for the special characters. So let's say pandas replace special characters. So here you can use regular expressions sometimes to look for special characters. Let's see if we So in regular expression, so maybe we can go back to the way we did it before. We'll just use a string replace. And last time, remember, it said, so here, let's apply the same thing. And, okay, so replace, so in regular expression, whenever you're looking for a non-word character, then you say \w, and you can look for regular expression syntax. Regex word character. So if you go in, you'll be able to find the slash. So you see the /w basically says, so it's searching for non-word characters in a string. So you can look for something that's non-word like this, and then let's just replace that with nothing. Okay, so let's do that. So now you see previously there is a period, and here now we don't have a period. So this way we've done a little bit of cleaning up. We've so let me put a little description here. Okay, so here we replace spaces and characters. All right, now that we've done some prep, now we have this, but it would be, before we process this any further, we also need to make sure there's no null value. So let's go ahead and say that is null. Right, let's just count and see if there's no. Okay, so in this new data frame, we're mainly looking for description, right? We only care about description at this point. So there's 1400 or so nulls, so we'd want to drop the nulls because that doesn't really give us much information. So let's do a drop NA and in place. Okay, so that way we are replacing it right in. So now if we look for how many nulls there are, yeah, no nulls, right? Perfect. So now we have a data frame that has no null values in their clean description, and all the string values are with underscores and without periods. Realize that these names are very much, indexed. If you have, so you really need, very clean descriptions to be able to do this type of bundling. Okay. If you don't have clean descriptions, let's say you have typos sometimes in the names or things like that, you might have to go ahead and clean that as well. All right, so it would also be okay. So now that we have invoice number, right, and then within this invoice we have this clean description, we're essentially ready to start doing what is this bundling process. But let's go ahead and think through how we're actually going to do it in an example. Okay. Switch over here. Right. So so suppose we have an example. So we have 5 invoices. So you can even think of these as shopping carts. Okay. So suppose we have invoice and then we have some item. Okay. So we have in invoice 1, somebody purchased item A, B, and C. So this is all in invoice 1. And invoice 2, they purchased A, C, and D. Okay, so we're essentially just creating an example of what we had before. And then B, C, D in invoice number 3. Invoice number 4 is A, D, E. And finally, invoice number 5 has 3 items, B, C, E. Okay. So small example showing, and think of these, right? So these are all, each one of these is an invoice. Or if you're e-commerce, then you've got, right, a shopping cart, right? Each of these shopping carts. So it could be the same user, it could be different users, but you really only care about when these items that were purchased all together. Okay, so the important thing is for this type of analysis, whenever you are bundling, you really need to know whether it was on the same invoice or not. Okay, that's because bundling means they were in the same invoice. Okay, so the first thing that we would want to do, so we really want to find out whether so first of all, let's clean this up a little bit, right? That's we have all of these in rows, but we really want to consider only one row per invoice and then put all of these together. So one kind of simple cleanup that we could do is to take all of this and then just put it into something like this. So we got invoice 1, and then we have A, B, C. Invoice 2 is A, C, D, right? And then B, C, D, A, D, E, and then B, C, E. So this is just to take whatever is in this huge table and put them in lists. So this is kind of like a list grouped by invoice. Okay. And now that we're able to look at it this way, let's take an example of a specific rule that we may want to generate. So a rule, so let's say we want to find out what is the, suppose somebody bought item A, then, should you recommend item D or not? Okay. So for this rule, let's go ahead and do some calculations. Okay. Let's calculate to see what is the probability of both A and item D showing up. Okay. If we look at all of these invoices now, A and D showed up here in invoice number 2, and A and D also showed up in invoice number 4, right? So that is essentially, just in probabilities, that's 2 invoices out of 5, right? So that's 2 out of 5. Okay, all right, then so this and now we want to know what is the probability of D, of somebody purchasing item D, given that they have already put item A in their cart. Okay, so we know that this definition of conditional probability, right? This is a conditional probability, is probability of D and A divided by the probability of A. This is simple conditional probability, and so that can be written as, I'm just going to put a line here. And that is, so D and A, we just calculated that to be 2/5 divided by probability of A. How often does A show up? 1, 2, 3, right? 3 out of 5. 3 out of 5 invoices, A showed up. So this ratio now, 5 and 5, so this is 2/3. Okay, value of 2/3. So essentially we've calculated, given that somebody has already put item A in the cart, probability that they would also get D is, 2/3 probability, right? So this is pretty much all that's happening in this entire process of deriving. So in terminology, this is known as an association rule. Okay, this is a rule that we are trying to, an association rule. How often do both of these show up in this is the support. And the support matters because if this combination only happens, extremely rarely, then there might not even be any point trying to calculate the probability, right, of D given A. So you want some minimum support, right? That means it should happen, some proportion, some acceptable proportion of the time. And then when that happens, this conditional probability is known as confidence. Okay, so these are all just pure terminology used by this method of bundling. Okay, and so like I said, this is called association rule mining. And so what we want is to be able to take a data set that's like this here on the left that we have, and prepare it to be in this list form, and then from there start generating these rules, and then calculate the support and confidence. And then you want to be able to, whenever somebody puts an item A in their cart, then you want to look for among all the other items. By the way, there's more terminology here. This is known as an antecedent. That means it's the first item, and this is known as the consequent item that you're gonna put in, right? Okay. So by the way, there's another sometimes you might hear the term lift. Okay, you might hear the term lift, and lift basically is a kind of like a, it's not a probability, it's a ratio calculation of this is confidence given that you know, given that A actually happened. Okay, confidence given that A actually happened. So this is just a ratio of 2/3 that we just calculated 2/3 here as confidence, and then the probability of A is 3/5. So this is 10/9. So this basically gives you how much of a boost are you going to get if you know, given that A actually happened, and that is so you might hear the term lift. We're not going to use it here, but if you hear the term lift, this is what we're talking about. Okay, so as you can see, this is just simple conditional probabilities. A lot of fancy terminology, but all you're doing is calculating probabilities. Okay, but in the process of, you know, for us to codify this, right? Here we want to take this, we want to convert it into lists, but maybe what we'll also do is transform that into a matrix form. So what we'll do is we'll create a matrix of, you know, invoices on this side for 5, and then, you know, A, B, C, D, E. And then, so invoice 1 is A, B, C, invoice 2 is A, C, D, right? So we're gonna do this transformation so that it would be easy for us to go ahead and then do all of this, okay? The main library, there's a, so this whole thing is called association rule mining. We'll go and execute that here in a second. So let's go ahead. Oh, by this, so antecedent consequent combinations, these are called frequent item sets, okay? So the methodology we're going to do is we're going to first take our data, put it in list form, then we're going to transform it into this matrix form so that it's easy to use, and then we're going to look for some libraries, and when we look for those libraries, after that we are going to first generate the frequent item sets, generate all the frequent item sets, right, that have some minimum support. And then for the ones that have minimum support, we're going to then go and calculate the confidence and then sort them by the ones with the highest confidence, so that finally we would say, okay, give me the ones with the highest confidence with some minimum support and tell me what that rule is, and I'm going to use that for future recommendations. Okay. All right. So let's go back to the code here. All right. So we wanted to convert it from, so we're still in table form, and we want to convert it into list, and we only care about invoice and the clean description. So if we were to do, let's say, vendors group by with list. So in a group by, and then we also want to create a list out of that. So here somebody's asked this question. You want to group it by something and then provide a list, right? So this is exactly what we want. So you can do a dot group by whichever column we want, and then do a dot apply. So we're going to call this dot apply function, and then say I want to get it in list form. Okay. So this is, maybe we'll just add this to the data prep section. So you want to convert to, so I want to convert it to list form. let's just say convert to list format. We have our data frame, and we want to group by. We want to group by just one thing here. Group by invoice number. We're going to group by invoice number, and then we want to take our clean description and convert that into a. So group by invoice number, and then take clean description, dot apply, and convert to list. And let's, because this is not a, this is a much simpler data frame now. Let's just call it retail list. Okay. All right, and then let's see what this looks like. Okay, so it takes a little time because it's trying to merge all of that, right? So, okay, cool. So we've got invoice number now, unique invoice numbers in every row, and then it's taking, it's put, let's see. So tea light holder, metal lantern. Okay, so it's got tea light holder, metal, white metal. So it's put that in a list, so you converted that to list form. Cool. So we are basically, we've done this step now. Now we need to do this step and then do the association rule mining. So let's go ahead and look for Python association rule mining. Here, this the algorithm, by the way, is also known as the a priori algorithm. Okay, I'll write that out in our notes. Yeah, but it's also known as the a priori algorithm. But the nice thing is there is a library called MLExtend. So we're not going to be using sklearn. We're going to be using MLExtend to generate these association rules because they've already done a lot of the work, and it's already pretty much automated. So let's go ahead and see what they've done. Okay, so first of all, generating association rules. Okay. So as you can see here, they use MLExtend, the library, and then they have something called pre-processing there, and they use this transaction encoder, and that transaction encoder does a fit and a transform to this data set, which is in list form, as you can see. So that transaction encoder takes this in list form and puts it into that binary form. So it's doing this step, that going from here to here. Okay. So let's copy that. So let's take this, and oh, by the way, so we are basically in another section now where saying build association rule mining mode. Right. So first, okay, we're doing the transaction encoding. So let's say here what we're doing is, let's say encode data as a transaction matrix from a list, right? Okay, so go to transaction encoder, and we already have this. We already have our data set. Initialize the transaction encoder, and then do a fit transform. And after that, we're going to store that in a data frame format. Okay, so those are the three pieces we need. Let's go ahead and do it for hours. Okay, so this is a transaction encoder. Let's do it the way with our terminology. Model retail transaction encoder. Okay, and I'm going to do a fit of my data set, and which is my data set here is my list. Okay. and that is basically in array form. So let me just say this is my conversion to array, and then done the fit and transform, and now I want to create a data frame out of it. So I'm going to pass that array in, and my columns are going to be columns of what I had here, what I used for encoding, and let me call that retail baskets. Okay. All right. So let's see. We can define the model for encoding to convert the matrix. We're doing the fit and transform. Again, why fit and transform? It's figuring out how many of these unique values are there, right? Converting them into columns, and then the fit is then basically so fit identifies how many columns there are. Transform is basically putting binaries in there and then converting that to a data frame. Okay. So if we do this right, let's see what that. Okay, so we have each invoice now as a row, and you can see falses. For every invoice, it's going to have a true for every item that that was purchased. But as you can see, especially when it comes to things like e-commerce, these are going to be very sparse matrices. Okay? Because there's so many. Imagine Amazon carts, right? There's millions and millions of items, and usually you're going to purchase 3, 4, or 5 items at a time. So there's going to be a lot of falses or a lot of zeros in here. Okay, but let's see how we're going to deal with that going forward. Okay, so now that we have created this, we're now at this stage. We've got this matrix, but we're going to actually do the association rule mining. Now we're going to come up with the probabilities. And let's go back here to copy the code. So this is known as, so that was pre-processing. Now we're doing getting the frequent patterns. Okay, the frequent patterns. Remember in our terminology, these are our these are our frequent patterns. How many that come here, and we're going to call them item sets. Okay. All right. So let's take that, and here this is where they call the frequent item sets and calls the FP growth subset within this library. Okay, so let's call frequent patterns. So for we want to say we want to determine the items and item sets with at least some support, some amount of support. Okay, X support. Well, let's try that here. Okay, so frequent patterns for this, maybe we only need a priori. Okay, and now we'll take this frequent item sets. Actually, let's do the a priori one first. Okay, so we're calling this so a priori is the name of the algorithm that is used to go calculate all the different support values and then filter them and then give us the frequent patterns. Okay. Right, and we'll call them frequent item sets. A priori, and our table is DFRTB. Let's do a min support because this is very sparse. I'm going to go with 1%. Okay, so we're saying at least 1% of the transactions or of the invoices should have those combinations, and those are the only ones we want to see as our frequent item sets. But also what I'm going to do is I'm going to, again, to time this to see how well it does. Okay. All right. Okay. So while this is running, I want to go and maybe start updating our decision, our tree here, not decision tree, but our cheat sheet tree of when should we apply, when does association rule mining even come into play, okay? So let's do that while the association rules are being run. By the way, the larger the data set is, the longer it's going to take to run because it's calculating all of those probabilities, applying filters and things like that. Okay. So remember how we said that, descriptive data science here on the top right, top left is mainly to do with statistics, business intelligence, and then predictive data science. You go through all of this and then you go down to machine learning. Well, we kind of skipped this step here. We went directly into target as continuous or discrete. But remember from last time, so what I'm going to do is I'm going to take this whole piece and move it down a little bit. All right, try that again. Okay, I'm going to move that down. Okay, so the part we skipped last time, because it wasn't exactly relevant, was that we assumed that we already had our data to be labeled. You remember when we have a column of data that the data is labeled. So if the data is labeled, you say data is labeled. That means you have a column with either the prices, home prices, or the tips, or we have a column that says whether somebody has heart disease or not, or there's a column that says what the digit is and all of that. We have that column, right? So this would be known as supervised learning, okay? Because it has already been supervised by the label that you have provided it. And when the data is not labeled, okay, when the data is not labeled, then that brings us to unsupervised learning. And so last time when we were looking at, so we've already done one piece in unsupervised learning, right? We had our retail transactions and we were trying to group our customers by behavior. And remember, there's no labels there, right? We had nothing to say whether a customer belonged to one bucket or another. So that was part of unsupervised learning. But within unsupervised learning, what we were actually trying to do was we were trying to determine the relationships between rows of the data. So think about it. We had a data set with, here you have customer, right? 1, 2, 3, 4, 5, blah, blah, blah. And we're trying to merge these together and merge these together. So we're trying to find relationships between rows, okay? And whenever you're trying to find relationships between rows, that is known as, actually go up one level here. Yeah, that is known as clustering. Okay, and under clustering, we of course did work with k-means. Clustering, we worked with hierarchical clustering, also known as agglomerative clustering, and we played with dbScan also, right? And if you remember, one way to consider using this is if we have a decently small enough data set. So let's say the data set is small, then we would go with hierarchical, because remember, it is going bottoms up, right? And we're not really defining how many clusters we have. But when the data set is large, or if you can assume that, so these are both of these also assume centroidal behavior, right? That means we have reason to believe that the points are around a central point. So location, for example, would be a good example. All right, so either the data set is large or small. If it has centroidal behavior, you might be in one of these two. But then if you don't have, you don't have that assumption of centroidal behavior, then or you want to detect anomalies, then you'd go with dbScan, which is also good at capturing non-centroidal behavior. Okay, so we already did clustering, and this time we are working on association, right? Where we are trying to determine relationship between rows and columns, right? So if we think about the data set here, we're not only going with, right, our invoices, but we also have items, and we're trying to look at relationships across both of these, right, and trying to put them together. So that is called association within unsupervised learning. And what we have done right now is called association rule mining. Another popular name for this is market basket analysis. So if you hear market basket analysis, this is the exact same thing. Okay? All right, and here, and there's other ways to do association that we're going to talk about later, but for now we only have that one, so we'll just leave it that way. Okay, all right. Let's go back now and see if our code is done running. Okay, so it took about a minute to generate these frequent item sets. Now let's see what they look like. Item sets. Okay, so we said we needed at least 1% support, right? So it also gives you individual item sets, right? Just an item of its own, right? How often does this item show up? How often does this? We're mainly interested in pairs or more, right? So you see this item, lunch bag skull plus some other lunch bag design, both together show up, more than 1% at the time. So these are all our frequent item sets. So now we have reached this point here. We've got our frequent item sets that satisfy certain minimum support. Okay, but one thing I also want to talk to you is that you see that it took a decent amount of time, and there is another method of generating these frequent item sets, and that is by using this FP growth. Okay, so FP growth basically is a mining method where, as you can see here, let's see. So it mines these frequent item sets by using densities. Okay, and it is better. It works much better when you have very sparse data, because a priori the function we just called generates all of the item sets and then filters them by support. Whereas FP Growth does it in a smarter way. It doesn't generate all of them. It looks for ones with decent support and only then generates them. Okay, so let's just run this with, so this was 55 seconds. Let's rerun this with FP Growth. And so why would you ever use it? Use a priori. A priori, is good if you again have a small data set. But in general, FP Growth should give you, better results most times. Okay, and then let us see how long this takes. 3 seconds, right, to generate the same set of frequent item sets. So as you can see, it helps to do it in a slightly more intelligent way. In the beginning, when I would use MLXtend, it only had a priori, and later on they brought in FP Growth. Okay? So that's why you see here, even in their code, they have FP Growth here, but they say you can also use a priori, FP Max. So FP Max is another way of doing FP, let's just go with FP Growth for now. So now that we have our frequent item sets, we want to calculate the actual rule. We want to define it more clearly as rules, because right now this is what we're seeing, right? We're seeing, hey, these are all the combinations you want to get, but we want to see, hey, if somebody buys one thing, what is the likelihood that they are going to buy the other thing? And that's the association goal part. Okay, so let's go ahead and get that here. So here's where it's actually generating the rule, and we are going to, and this is saying that among these frequent item sets, calculate the confidence and give me the ones that have at least some minimum confidence. Okay, so you remember how we said that we had to set a very low threshold of support because our data is sparse. However, when it comes to confidence, we can keep that pretty high, because we want to say, hey, okay, maybe people don't buy these items very often, but when they do, how often do they buy this other specific item? Okay. All right, so now we are ready to generate the association rule that show at least some X% confidence. So maybe let's go with 70% this time. Right? Okay, we've got association rules now. And let me call that, store that as a rules. I got my frequent item sets here, metric confidence, minimum threshold of 7%. Okay, so let's run that here. Let's see what the A rule will look like. Great. So what we're seeing here is the antecedent, the consequent. Remember, this is how we read this. If somebody purchases the playhouse bedroom, then they are likely to purchase the playhouse kitchen with a probability of 0.79, okay, or 0.8. There's an 80% chance they're going to purchase this, given that they've already purchased the bedroom, or they put that in their cart. Again, remember, these are bundling. This is before somebody hits the buy button. They put this in the cart. They're likely to put this in with an 80% confidence. And we can already see that it's already pre-filtered by support, right? So it would be nice to kind of put this in order of confidence, right? The most confident ones at the top. So that way so let's do that here. Let's just say A rules, let's sort it, sort values by, so we want to do it by confidence in this now. By confidence and ascending sorry, sending equals false. I want the highest confidence to be at the top, and so I'll just do it in place. Okay, all right, and then let's see what the labels look like now. Just sorting it so it's easier to read. So the highest confidence here is that when somebody purchases the pink teacup and saucer and this other item, Rose's Regency something, then there's a 89%, close to 90% confidence that they're also going to purchase the green one. Okay, teacup and saucer, and and this combination of all of these three show up a little over 1% of the time. Okay, so and then of course there's lift and a few other metrics here, but that essentially gives us exactly what we wanted, right? So now we know that when we have data where we have by shopping cart or by transaction how multiple items that you bought at the same time, then, and we don't really need to know how many of those, we don't need to know what the price is or who even the customer was. We just need to know that they happen at the same time. Then by using association rule mining, we are able to generate all the frequent item sets that occur at least X% of the time. And then among those, we calculate the confidence, the conditional probability of if you have some antecedent, then the probability of you getting the or purchasing the consequent item. Okay. All right. So with that, I'd like to do a few more things before we wrap up today. So actually, I think there's a slight typo here. So because so this in this case, let's go back here. Here we're saying that. Okay, no, this is right. Here we're saying, given that somebody has purchased A, what is the likelihood they're going to purchase D, right? Okay, yeah. So in that case, A is the antecedent and D is the consequent. Okay. For a second, I thought we had switched that up. Okay. All right. So let's. Just give me a minute here as we swap out. Let's go back to this here. Okay, so what we've also done now, we've got association down. There is another there's another type of unsupervised learning. I'm gonna just create a little bubble here for it, but I'm gonna talk about that here real quick. So, we've done some data pre-processing, right? So, there's always I always request my students to keep a cheat sheet, not just of what algorithms to use, but also what type of pre-processing to do. So I'm going to start another section here with a little bit of terminology. Okay, so suppose we have a let's see where I should put this because I might need that real estate. Okay, I'm going to do it all the way up here. Okay, suppose we have a data set that we have our data here, and we may or may not have a target depending on if it was supervised or unsupervised. But then we have our training set and our test set. And of course, you guys remember where we did cross validation, and we went ahead and split it multiple ways. And then in terms of evaluation, model evaluation, we had multiple choices here. Whenever we were doing regression, then we used the error calculations, like the absolute error or R squared or something like that. And then whenever we were working on classification, then we used the ROC curve and then the area under that and all of that. Okay, but what I want to call out here is what type of pre-processing have we learned so far? So, here we have our features, right? We have all of our features, and okay, so with respect to the features, we've done some pre-processing, right? Data pre-processing. And so what type of pre-processing have we done so far? We've done missing value handling, right? We know what to do whenever we have missing values. We either dropped an entire column if it was completely useless, or if it had some missing values intermittently. Remember, we did the forward fill, backfill, or use the mean to fill those rows. So missing value handling is an important part of pre-processing. And then we also did some data encoding, right? So we did some data encoding. So that was taking our categorical values, figuring out which ones of them are unique, and then using label encoding, using potentially even using one-hot encoding, and all of that to convert from our object type features, look for which ones have a small number of unique values, which make them categorical features, and then doing this data encoding to convert them into numerical values, right? So we've done that as well. And we've briefly done data scaling. So whenever we also want to always make sure that we do data scaling so that we don't have mismatch between the units of our columns. And so there we used pre-processing scale. We could use min-max scaler and things like that. So these are, I'm just giving you, these are things you should think about when you get a data set, right? So you could just think of this like a cheat sheet where you're saying, okay, did I handle missing values? Did I do any data encoding necessary? Do I need to scale my data? And there is one more thing that we haven't done yet, but whenever you guys, towards the end of this course, we're going to do a project, and in that project, you're most likely going to have to do data balancing. Okay, so data balancing basically means that if in your classification, suppose you have an overrepresentation of one class and an underrepresentation of a different class, then you want to balance the data. If not, the model will basically just mostly predict one class and ignore the other one. So you really want to do some balancing. Okay? But why am I talking about this now? Right? So we do this type of data pre-processing whenever our features are incomplete or or not ready, right? Or not ready for modeling yet. Okay, but on the feature side, there's also sometimes you just have too many features. Okay, so think of our digit recognition problem. Well, that had 10,000 columns. But some of these problems, whenever you're doing especially in the classification side, you could have hundreds of thousands or millions of columns, and so there's some pre-processing that you need to do, because if you just feed that in, your model is going to choke. So that now we have something that you do called, this is still comes under, something that you should think about is dimensionality reduction. Okay, this basically says that I want to reduce the dimensionality of my data. I just have too many dimensions. Okay, so that I'm going to talk about that a little bit today. We're not going to have time to go into an example of actually doing it, but it's something that you need to think about. So there are two methods of dimensionality reduction, and mind you, these two methods are constantly confused with each other. Okay, so I'm going to talk about them and then explain them in detail. So there is something called Principal Component Analysis, or PCA, as very, very, very commonly used methodology out there. And then there is factor analysis. Okay, and majority of the students I work with in the beginning have no clue what the differences are, right? Because it's always like, well, I apply those for dimensionality reduction. Yeah, but why do you apply them, and when should you apply them is the question. Okay, so just going to give a brief description here, and then we're going to separate those out. So PCA versus factor analysis. Maybe I'll go back here in space. Okay, so we've got, let's talk about PCA versus factor analysis. Okay. So in both of these cases, you have too many columns, right? You have too many columns. But when we are thinking about PCA, so suppose I have columns, I have columns x1, x2, x3, x4, okay? And I have many, many, many columns of these, right? Too many. Then if I believe that the contribution that these provide can be linearly combined into a new column, okay? If I feel like they can be linearly combined without losing the information that they have, that is known as principal component analysis. So you would calculate C as C would be W, so like some weighted sum, okay? W1 x1 plus W2 x2 plus W3 x3 plus W4 x4. So it's just it's because I feel like I won't be losing that information, okay? So you could almost think of it as, right, x1, x2, x3, x4, and all of your columns, and you are combining them in some way with weights 2, 3, 4 to get your new column C, right? And so you're able to aggregate many columns into fewer resulting columns, okay? That's what you're doing here. All right. What happens in factor analysis then on this side? Well, in factor analysis, you still end up with reducing your dimensionality, but it's because of a different reason, okay? And so in factor analysis, suppose you have columns x1, x2, x3, x4, and so on and so forth. You feel that there is some other underlying factor that is driving all of these. and it's driving them in different ways. So it's an underlying factor. So take an example of, suppose we measure, nervousness. Okay, suppose this is like a psychological data set. So how nervous is somebody? Okay, or how they the volume of their sound. Sorry, the volume of their speech. Okay, how loudly they are speaking. So volume of speech. Then their facial expressions, right? So we're able to measure those, but we realize that all of these are probably coming out of some other underlying factor. So that's where the name factor comes from. Some underlying factor, okay? And hold on one second here. Sometimes my pen stops working. Okay, all right. Back. So you have an underlying factor here that is resulting in nervousness and then the volume and your facial expressions and things like that. And so an example of a factor might be, it might be social, your social anxiety, okay? Or it's your social anxiety that is causing you to be nervous, that is causing your volume to go down, that is causing your facial expressions to change. But it's hard to measure that. We don't have direct data to measure that. We can only measure, these nervousness and volume and things like that. So when we believe that there's some underlying factor that is driving these, that is when we apply factor analysis. So F will be, so what you would do is you'd say, okay, I'm going to write X1 as F. Let's put some kind of weight here. Use something other than W. So let me say B1F. And then we'll have some kind of error term also. So U1. And then X2 is B2F plus U2. X3 is B3F plus U3. So you see that we are going the other way now, B4F plus U4. So we are trying to find what generic value of F that you can just apply some weight on to that value and then end up with all the different columns X1, X2, X3, and X4, okay? And with some kind of error term. So if you want to pictorially draw this out, you basically have X1, X2, X3, X4, but you have arrows from the other direction, right? You say how here on this side, you have arrows from X1, X2 to your principal component C. Here you have arrows the other way. So here you have a factor that is used to come up with, can you come up with some F that if you apply some weights, get you the values X1, X2, X3, and X4, right? And then of course you have your, all of your error terms, right? So hopefully that, simplifies that explanation and you make sure that you don't use these interchangeably, right? In both of these cases, you still end up with fewer columns, right? So in PCA, instead of x1, x2, x3, and x4, you end up with a new column C. In factor analysis, instead of these 4 columns, you end up with a column F. So fewer columns, but completely different reasons, right? So hopefully that makes sense. And if we go back to our intro, that is when, so you would use PCA if you have many features that can be aggregated together, right? Simply aggregated together through some sort of linear relationship, then we say, hey, all these columns are not really giving me any more information, so I can combine them. Whereas in factor analysis, there's some root cause factor or root factor that is causing many features. Okay, so with that, I think that's all the time I'm going to spend on that. You could look it up more. There's simple libraries that do both PC and factor analysis. I really want to make sure that we know when to use. All right, so both of these fall under dimensionality reduction. And when we come back here into unsupervised learning, a lot of times you will see a dimensionality reduction also talked about under unsupervised learning. Okay, although it's really a pre-processing step, right? It's really meant to prepare your data before you do something, but because there's no labeling, I guess it's put under unsupervised learning. And the way I think of it is, why it's okay to put it under unsupervised learning is, you see how clustering here, we said that we are determining relationships between rows. Well, in dimensionality reduction, we are kind of determining relationships between columns, right? We're trying to figure out which columns are related to each other. And so, you can think of PCA and factor analysis. And, they don't necessarily give you direct output that you could use. Maybe factor analysis may be useful for something like root cause analysis, type of results you're looking for. But of course, there's other ways to do that, which use factor analysis. So I wouldn't typically call this as a major type of unsupervised learning, but it's more of a data pre-processing step. Okay, but for completeness, let's put it here. And when you go out there, even if you see dimensionality reduction as unsupervised learning, you know that it's mostly meant for pre-processing. Okay. All right. So with that, we'll wrap up for today.